Hello everyone. We were supposed to start principle of virtual forces today, but we discussed principle of virtual displacement as the originally proposed by Bernoulli. That is the principle, that was the original version of principle of virtual work. And then we discussed, then if we want to apply principle of virtual work in structural mechanics problem that we are interested in, where the bodies are deformable, we need to move beyond that. We need to generalize the concept, and in that generalization we need to include the concept of virtual forces, and then which eventually gives us the principle of virtual forces, and then deformable bodies, since we need to consider both external and internal work. But before we do that, let us first demonstrate principle of virtual displacement through some example, how the principle of the virtual displacement can be used to analyze at least some part of the analysis of statically determinate structures. Okay. Now, and then the principle of virtual forces will be discussed in the next lecture, means lecture 14. Okay. So today what we will do is we discuss what is principle of virtual displacement, and we will see some example of that. And principle of virtual displacement, if you remember, it says that if an object is in equilibrium, if a rigid body is in equilibrium, then and if it undergoes some small virtual displacement, then the total work by the actual forces, external forces acting on the body, which moving through a virtual displacement is 0. Okay. And now let us see the first example. So these examples we have already used. We have already probably used for drawing bending moment and shear force diagram. Let us now and when we try to draw bending moment and shear force diagram, defining the internal forces, we had to determine the support reactions, and there we use support reactions. We determine the support reactions using equilibrium. Okay, equilibrium conditions, or the principle of statics. Okay. Now what we do is we try to find out this equilibrium equation using the concept of virtual displacement, principle of virtual displacement. Okay. The first example is this. This example is it is a beam, a simply supported beam with overhang. This is okay. Let us draw it. Let us take some more space, because let us draw it here. This is roller, this is hinge support, and then we have another roller support here, This is A, this is say B, and this is point C, and this distance is L, and this distance is L by 2, and it is subjected to a force P. What we need to find out? We need to find out the internal. We need to find out what is the support reactions. Okay. Now, since we are applying now the principle of virtual displacement, which we have already discussed for rigid bodies, so we assume that the body, the member AB is rigid body. Okay. Now, but as I said, in actually we are also interested, along with the internal forces, we are also interested in the deformation of the body. Then in order to find out the deformation, we need to move beyond the assumption of rigid body. That we will be doing in the principle of virtual forces and in the subsequent lecture. But for today, when we apply the principle of virtual displacement, we assume this is a rigid body, because we are not interested to find out the displacement, we are only interested to find out the reactions. Okay. Now what the reactions will be? What reactions will be? If you straight away you can say that the horizontal reaction at A is 0, because it is because there is no horizontal force. So there will be a reaction there will be a reaction at AY, which is AY, and then there will be reaction here at BY, right? This is CY. Okay. Now so we can so this is the so what are the force field we have? The force field we have is reaction AY CY. When we draw this reaction, we can remove this support condition, we can remove this support condition. So, this is the force field, okay. This is the force field, this is the force field. Now, we need to construct the displacement field of now what we have to do is we have to apply a virtual displacement in this body, okay. Now, let us give some virtual displacement, and suppose let us do it here itself. First, let us give a virtual displacement like this. So, virtual displacement, not necessary that they have to satisfy the constraint. The only thing the virtual displacement needs to satisfy the internal compatibility, and in this case since it is rigid body, now if we give a virtual displacement, if we give a rotation like this, then it will be a rigid rotation, okay. And suppose this distance is delta. This distance is delta. Okay. Now, you see, this is displacement field. Okay. This is displacement field. Now, this is displacement field. This is displacement field. Okay. Now, what the principle of virtual displacement says, that if we have a virtual displacement, these are the forces acting on the body, the real force, actual force acting on the body, then the work done, or the product of the actual force and their conjugate displacement, this is the conjugate to this force, the product of the force multiplied the product of the force and the conjugate displacement, the summation of that, which is the virtual work, that is 0. So, what is the virtual work then? Then virtual work W is equal to, now you see, at this point there is no displacement in the direction of AY. So, AY will not contribute anything in this work. Now, if this is delta, then this distance will be 2 by 3 delta. This length is L by 2, this length is L. So, then what would be the force, what would be the work done, what would be the product of Cy into this? It is the virtual work by this force, and then what will be the virtual work by this force? Virtual work by this force is P into delta. Now, this displacement and the force, they are in the same direction. So, it will be if we take, so this is positive, and if it is delta, now force is in downward direction, it is in upward direction. So, this is negative. So, now then what would be the contribution? Total force will be that 2 by 3 into delta into Cy, and then minus P into delta. This is the total virtual work, and virtual displacement says that this is equal to 0. So, this gives us Cy is equal to 3 by 2 into P. By just equilibrium equation, you can verify what is the value of Cy. Okay. Now, next we need to find out, once Cy is obtained, we need to find out Ay. We won't be using equilibrium equation, right? We will be only using this principle. Now, let us find out reaction at A. Again, draw this beam, simply support it at A, and then roller support at C. This is A, B, C. We have force at this, force here P. Now, what we do, give a displacement like this, virtual displacement, or let us, now this length is L, this length is L by 2, and if this distance is delta, then this distance become delta by 2. Okay. Now, we have in the force system, we have a force Ay here, and then Cy here. Now, what is the virtual work? Virtual work W is equal to Now Cy, there is it is rotated about Cy, so there is no displacement at Cy. So this virtual contribution from Cy will be 0. Contribution from Ay will be Ay into delta, and then contribution from Py will be plus P into delta by 2. Now P and delta, they are in the same direction, it is positive. Ay and delta in the same direction, this is positive. This is equal to 0. Now if this is equal to 0, then this gives us Ay is equal to we have minus P by 2. Okay. So support reactions are Ay is equal to minus P by 2 and Cy is equal to 3 by 2 P, and we, in order to get this support reaction, we have not used equilibrium equations. What we have used, the principle of virtual displacement, which is in some way is essentially a different form of equilibrium equation, right, that we have seen, because this is valid if the object is in equilibrium, right. So this was the first example. Now take one more example. This example, this is again a statically determinate structure. Because of this hinge, it is statically determinate structure, internal hinge. If you do not have hinge, it is a propped cantilever which is statically indeterminate. Now again here we have to find out what is the corresponding what is the reactions. Now how many reactions we have? We have vertical reactions at C, and then vertical horizontal reactions at A, and moment at A. Again draw this. This is A, this is a point A, okay, and then we have an internal hinge at point B, internal hinge at point B, and then this is point C. This distance is 12, and then in addition to that we have a force here, P here, and then a moment at this is M. Okay. Now and then this distance is L, this distance is L here, this distance is also L, this distance is also L. Okay. Now what are the forces we have? The forces we have is here we have here which is Cy, which is the vertical, which is a roller support. Then here also we have Ay, and then Ma. Okay. We assume there is no horizontal force, so there is no Ax is equal to 0, so it is not shown here. Okay. Now we need to find out, we have three unknown here, one is Ma, Ay and Cy. Now we need to give the virtual displacement in some way that this unknown can be determined. Okay. Now first give virtual displacement like this. Now, and again the virtual displacement should satisfy the internal compatibility. It is not that we have to satisfy the constraint as well. Now give virtual displacement here is something like this, okay. Means point A to B, there is no displacement, and since point B we have hinge here, so this part, the part BC, can rotate like this, okay, and this satisfy this compatibility, this displacement. So actually your displacement is this. So this displacement is compatible, right? They satisfy the compatibility. Okay. Now suppose this is delta. This is delta. Now if this is delta and this angle is theta, then we can say that theta is equal to or delta is equal to delta we can write is equal to theta into L, right. This delta is equal to theta into L. Now see what are the, let us write the virtual work. The virtual work W will be, what are the contributions we have from this? W will be, see at point A there is no translation, no rotation, so the contribution of Ay will be 0, contribution from My will be 0. At C there is a translation of delta which is in the direction of Cy. So Cy will contribute, and that contribution will be Cy into delta, and then we have Then we have a moment, and then associated the associated displacement for the moment will be theta, and that will be minus m into theta. So, that is equal to 0, right. Now, delta is equal to theta into L. If we substitute delta is equal to theta into L, what we get is Cy is equal to m by L. Cy is equal to m by L. Okay. Now, so this we obtain from this virtual work, and if we take this virtual displacement, if we give this virtual displacement, then other unknowns cannot be determined. Now, let us find out other unknown. Let us find out what is the moment at A. So, again take the same problem once again, same problem, and give a virtual displacement like this. Since at B there is no rotational constraint, so it can take the form, the virtual displacement is still, this virtual displacement is compatible. And suppose this angle is theta, if this angle is theta, this angle become 2 theta because of this because of the length given here, and then corresponding this distance become 2 theta into L. Okay. And then we have a moment, this is the moment we have, and then another moment here, this is another moment we have. Okay. And then force, the force here. Okay. Now, and then Ay, there is a force Ay as well. Now, because of this virtual displacement, Ay will not contribute, M will contribute, this M will contribute, this is Ma will contribute, this M will contribute, and P will contribute. And if we take the total virtual work W will be minus Ma into theta. Okay, that is how we defined theta. Theta is and then contribution from this is plus. Okay, that is how we define theta, and then contribution from they take this as minus, and then minus P into this is up, P is downward, this is upward, minus P into this distance will be if this is 2 theta L, this distance will be theta into L. So, P into theta into L, and then plus this, and this will be 2 theta into M, that is equal to 0. Now, in this case, if we that is equal to 0, so this gives us Ma is equal to 2M minus PL. Okay. Ma minus PL. So, this is the corresponding this is the moment at A. Again we obtain this moment not by any equilibrium condition, by applying the virtual principle of virtual displacement. Now, we need to find out what is Ay. So, we have to give the virtual displacement in such a way that we get the contribution from Ay. Now, let us give the virtual displacement like this. Again, this was this is the internal hinge. Okay. This is A, and then this is C, this is P, this is B, and we have the forces like this. This is Ma. When you write this, when you sum them, please make sure what sign you take and be consistent with the sign. Okay. And then we have from Cy. Let's give a virtual displacement like this. And then this is hinge. The reason this virtual displacement, this is delta. This is delta. The reason why this virtual displacement is given, because you see there is no rotation between AB. So, the contribution from Ma will be 0, and there is no displacement at point C. So, contribution from Cy will be 0. Here we get only contribution from Ay. So, this is the virtual displacement. Again, it not necessarily not necessarily need to satisfy the constraint. Only thing is it should satisfy the internal compatibility of this member. Okay. Now, if this is theta, then we have another force here. This is P, and then we have another moment here which is m. Okay. This distance is also so delta will be equal to, if this angle is theta, and this distance is L and this distance is 2L, this distance become theta into L. So delta is equal to theta into L. Okay. So write virtual work. So virtual work will be AY will contribute. So AY into delta is equal to theta into L, and then M will contribute. This plus M into theta, and then P will contribute. Contribution from P will be minus P into theta into L, delta is equal to theta. So that is equal to 0, and this becomes AY is equal to, AY becomes P minus M by L. You verify verify using equilibrium equation, you get this value. So let us quickly see. Now you see here, please make sure the sign. The reason sign is because of the action of this load. Because of the action it load, by intuition you say that it deflect, it can cause deflection like this. So this and this moment and this theta, they have the same sense of direction, right? So that's why this is positive. But in this case, they have this m and this theta, they have a opposite sense. The direction is in opposite sense. That's why it was negative, right? Similarly, this ma and this theta, this ma would have caused deflection like this, but now we have assumed displacement, virtual displacement like this. So this ma and theta, in terms of directional sense, they are not in same. They are not same. That's why it is negative. Okay. So you take the sign properly. So what you do is you apply the equilibrium conditions and verify whether the support reactions that we have obtained from principle of displacement are virtual displacement, right or not. Now what we have actually used here, this is fine, this W is equal to 0. Now in addition to this W, all the contributions that in this expression we have, those contributions we have obtained from simple geometry, right? For instance, if this is theta, this has to be 2 theta L, this has to be 2 theta. These values that we obtain, that is simple geometry, right? Similarly, in this problem as well, if this is delta, then this should be 2 by 3 into delta. That also we have obtained by using simple geometry. Means what we have done here is, now these are the two problems that we have addressed, that we have just now attempted. Now finding reactions, suppose a problem is given, we need to find out the reactions. This is essentially a problem in statics, right, where we need to, if it is determinate structure, then we need to draw the free body diagram. That's what we learned as of now. If you forget what we are doing right now, at least till last week, what we learned is, if we draw the free body diagram of the object or the entire object, then apply the equilibrium conditions on the free body diagram and get the reactions. So this is essentially a problem in statics, right? What we have done here is we solve the problem in statics, but not using the equation of statics. What we have used is principle of virtual displacement, but the contribution, each term in that equation, in the virtual work, that equation, each term we obtain from simple geometry, right? So essentially what we have done is, the principle of statics are solved through geometry, and that's what principle of virtual displacement allows you to do so. Now when we talk about principle of virtual forces, then you will see the virtual force is just, the principle of virtual force is just the opposite, where the problem of geometry will be solved using the concept of statics. Okay, but that will discuss in detail. So we stop here today. What we have learned so far is we learned what is the concept of virtual work, what is virtual displacement, then what is the concept of virtual work, and then principle of virtual displacement, and how what is the principle of virtual displacement, what is the principle of virtual work for a rigid body, and then how that principle of virtual displacement can be used to determine support reactions for rigid bodies. Okay, but this capability is not enough. This understanding is not enough to solve the problems that we have to in structural mechanics. Therefore, we need to go beyond. We need to extend this principle. We need to generalize this principle, and that we will be doing in the next class. Okay, then I stop here today. I see you in the next class. Thank you.